So, we have seen so far how we can make our processors faster by using concepts of pipelining, superscalar, VLAW, this kind of concepts. Now, these have become very standard concepts nowadays. So, whenever you buy a computer system with an embedded processor, you will see invariably these technologies are built into that as a standard feature. Okay. Now, the question comes, if you look at the modern processors which goes inside our desktops and laptops and also our mobile phones today, you have heard about multi-core processors, multi-core computation. So, what it is? Multi-core essentially means I have the capability of fabricating larger systems on a VLSI chip. I am fabricating more than one processors inside the chip. That is very roughly speaking the concept of a multi-core. So, the question arises, why we are actually going for multi-core? Let us try to address these issues in this lecture. So, our topic of discussion is multi-core processors. Fine. So, as I said, a multi-core processor is nothing but a processor system which consists of two or more CPUs. CPUs are typically independent CPUs, they are not strongly connected or they are not dependent on each other. They can independently execute or process different independent programs if required, right. They are independent in some sense. So, for a multi-core processing system, we have two or more independent cores or central processors. These CPUs are called cores. Now, these cores, they come inside a single package. You can buy, for example, you can buy a Core i3, i5, i7 processor from the market. So, inside the same package there will be multiple cores, 2 or 4 or 6 whatever. Now, these cores or processors, they are all fabricated inside the same die within the chip. So, there are two alternatives. So, you can either have a single die, die means a silicon where the chips are all fabricated, the circuits are fabricated, or in modern day processor packages, VLSI packages, you can have multiple dies which are connected or bonded together inside the same package. So, you can have either of these two, but the thing is that these multiple cores are inside your same package. You buy a VLSI package, a chip, inside the chip there are multiple cores or processors. Now, typically speaking, if you look at the modern processors, the level 1 and level 2 caches are private to each of the cores, but however, the level 3 cache is common. This is shared by all the cores. There are symmetric systems where all the cores are identical, like the Core i3, i5, i7 multi-core processors which you use in our processor systems. These are called symmetric, they are all identical. But in asymmetric multi-core systems, the cores may have different functionalities. Well, you think of the multi-core systems that goes inside our mobile phones. Now, you have heard of quad core, octa core processor, there are 8 cores, but there is no reason to believe that all those 8 cores are identical. They have some specific purposes. Some of them may be specific DSP cores, digital signal processing cores. Some of them may be specific processor cores like ARM or some kind of architectures. Some of them may be doing some specific functionalities. So, they may be running at different clock frequencies, different instruction set and different capabilities. Okay? That is called asymmetric. Fine. So, why we go for multi-core? Now, you see, you have earlier heard about Moore's law. Moore's law says, this is an empirical, you can say, prediction. It says the number of transistors or gates that you can put inside a single chip will grow exponentially with time, will double approximately every 18 months or so. This was Moore's law, right. Now, Moore's law somehow has been sustained till now, but regarding the performance demands there have been some constraints. Like, although you can potentially increase the frequency of the clock, but you are unable to do so. Why? Because your chip power consumption directly depends on the clock frequency, and if you increase it, your power consumption can become unmanageably high and your chip might be burnt out. So, you will have to limit your clock frequency within a manageable level simply to tackle the power consumption issue, okay, not due to anything else. So, there are two possible solutions you can think of. The first solution can be replicate hardware. So, you use two computer systems that are running side by side and run them at a lower clock. Like, for example, just compare a core that is running at 3 gigahertz clock and 2 cores running at 1.5 gigahertz clock. Both of these will be having the same performance, but the second one will be having much lower power consumption, because power increases in a superlinear fashion with increase in the clock frequency. Okay. That is why you will see that in the modern generation of processors, although the number of transistors is increasing, number of cores are increasing, I mean over the last 10 years or so, the clock frequency has not increased much, that 1.5 to 2.5 gigahertz, it still remains within that level, okay. It does not increase that much. So, talking about the parallel architectures, a very rough classification, this is sometimes called Flynns classification, goes like this. So, we categorize depending on the instruction streams and data streams. First is representative of the traditional single processor or uniprocessor systems. This is called single instruction stream, single data stream. This means, pictorially speaking, I have a computing system where single instruction stream means instructions are coming one by one, I1, I2, I3 like this. Data stream means these instructions are operating on data, data are also coming sequentially one by one, D1, D2, D3. Suppose I1 is working on D1, I2 is operating on D2, I3 is operating on D3 like that. This is called single instruction stream, single data stream, SISD. The second classification says multiple instruction stream, single data stream. So, conceptually how does it look like? Multiple instruction stream, single. So, it says that I am feeding several instructions to multiple instructions. Let us say I11, I12, I1m. So, I feed m instructions together, then I feed I21, I22, I2m and so on. But it says that they are working on single data streams. Like this m instructions are working on this on single data. Well, conceptually speaking, it is a little difficult to visualize this kind of computation. So, where do we have a single data, but multiple instructions are working on it? You very rarely have it. Okay? So, strictly speaking, no real systems are there that can fall under this MISD category, very strictly speaking. But some people argue that pipelined processing. See, in pipeline processing you can argue like this, that well, let us say the MIPS 32 pipeline, there are 5 stages. So, you can say that there are 5 instructions that are executing in different stages at the same time. So, as if there are multiple instructions, they are working on the same data set, it is not individual data, they are calling a data set for a program, it takes some input data, it produces some output. That input data, you can argue that it is a data set. So, like this you can argue that a pipeline processor can be considered as MIST, but strictly speaking no, right. So, this is what is mentioned here, and single instruction stream, multiple data stream is something which you can correlate with vector processors, which we discussed in our last lecture. There a single vector instruction operates on all the elements of a vector, single instruction, multiple data. This is so called SIMD. There is another kind of architecture we do not see that much today, vector processors are much more predominant. There was initially some computers called array processors, where instead of arrays, instead of vectors of numbers, you could have arranged the numbers in the form of an array, typically 2-dimensional array. But nowadays you do not see that kind of a computer architecture anymore. And lastly, these are the true parallel computer systems or parallel processors. This says multiple instruction stream, multiple data stream. So, the multicores can fall under this category. There are 4 cores, 4 instructions can be executed at the same time, and they might be working on 4 different data. Okay. So, broadly speaking, this is one way of classifying computer systems depending on instruction or data stream parallelism. Okay. Fine. So, let us look at single core computer, the one that falls on the SISD category. Well, the example that I have taken is something similar to what we see inside our PCs, our desktops, but not the desktops of today, desktops of earlier years where there were single cores, the Pentiums. Now, this is a typical architecture that you used to see. This was the CPU chip, which consists of the arithmetic logic unit, registers, some other circuits, bus interfaces, and there was something called IO bridge. This IO bridge had 2 purposes. It interfaced the CPU with the memory system. This was a very high speed bus, and there was a relatively lower speed IO bus. This IO bridge also interfaced this IO bus with this, so that the IO devices could transfer data to main memory, and maybe the CPU can also access some of them. So, the IO bus had connections to some USB controllers, which provided some USB ports through which you can connect a variety of devices, mouse, keyboard, many others. Graphic adapter, you could connect your display monitor. Various disk controllers, you can connect your disk subsystems, and there were expansion slots. So, you could add some more devices like network adapters and others, right. This was a very typical kind of an architecture, and this was your single core. So, single core, this is a blown up picture of the same thing. This is technically the core, and this is the interface to the external world, right. So, when you talk of a core, so every core essentially consists of a register file, arithmetic logic unit, and of course, some control unit. The control unit is not shown here, the control circuits are also there. Well, this is a typical motherboard architecture with the terminologies that are used are shown here in a desktop PC. Well, the processor comes here. The processor is typically connected to a chip that is called the north bridge. This is a very fast switch. What does it do? This north bridge interfaces the CPU with the memory bus. In the memory bus, there can be memory slots. So, in the slots you can plug in your memory modules. There are memory modules of various capacities, you can plug those memory modules depending on how much memory you need. Okay. And on the other side, you have a PCI Express bus, which is typically used to connect high speed graphics for your monitors and other things which need very high speed data transfer, you have this PCI Express bus. And on the other side it is connected to another switch, this is called South bridge. This is of a relatively much slower speed. South bridge interfaces with so called PCI bus, which consists of several slots, PCI slots, through which you can connect network adapters and other things, different kind of circuit boards, and there are also direct connections available in modern motherboards, which has connections to network interface like Ethernet, disk interfaces like SATA, USB, then audio interface, and there is another bus which is meant for low speed devices. This is called LPC or low pin count bus. This is typically a serial bus working at a much lower speed, like serial parallel ports, keyboard, mouse, this kind of devices are connected here. So, this is the rough picture of the motherboard of a desktop. Now, I am showing you pictorially one of the motherboards here. You can see this is your processor out here, and this part you see, this is your north bridge, and the fins that you can see, this is actually heat sink. This is a very high speed chip, this dissipates lot of power. So, you need a heat sink to dissipate the heat, and this small chip out here, this is your south bridge. These are the PCI slots, these are the memory slots, okay, and the other components. You see, this is a motherboard which used to be several years back, but if you see the motherboard of one of the modern day PCs, you will see that many of these circuits have been collapsed into a single chip. There are very few chips and a very small motherboard you will see in the desktops that are available to. That is why it is possible to squeeze the size of the computer system that much today. So, you can have a desktop system where your entire processing cabinet can be so small, as small rectangular box, it fits everything there. Okay. Such machines are also available. Okay. Now, coming to multi-core architecture, conceptually speaking, okay, we looked at one core, right, consisting of a register file, ALU, basically this plus control. Now, for multi-core you have several such, and you have a some kind of a fast bus interface using which they can communicate among themselves, and there will be an interface with north bridge memory, the outside world. Okay. This is what you have, but this is a very generic picture. Let us look into some more specifics, that exactly how it works, how it happens. Broadly speaking, this kind of multiprocessors can be classified as either tightly coupled or loosely coupled. Tightly coupled means the processors or the cores, they have access to common shared memory. In other words, these processors are all inside the same box. So, inside the same box there are the processors, there is also the common shared memory. So, when you buy a computer system, you buy the system along with all the processors and also memory. So, inter-processor communication can take place through shared memory, like one of the processor can write some data into the memory, the other processor can read the data from that memory. So, the standard multi-core architectures usually fall under this category. But there is another kind of a multiprocessor architecture that is also available. This is called loosely coupled multiprocessors. This is sometimes called clusters or cluster computing. This is an architecture that is somewhat loosely coupled. How? Here there is no shared memory. So, how is the memory organized? Memory is distributed among the processor, each processor has its own memory, and communication here is not via shared memory, but through some high speed interconnection network. There are processors there will be a very high speed interconnecting switch, the processors will be connecting via that switch. They will be sending and receiving messages from other processors. Okay. This is how loosely coupled processors work. Fine. Now, pictorially a tightly coupled multiprocessor looks like this. This is a very typical diagram. So, you can see the different cores. Now, each of the core is having its own instruction and data cache in level 1 and also level 2 cache. These are all private to the processors, but typically the L3 cache is common across all the processors, and of course, the main memory is also common. So, this L1 and L2 caches are private, L3 and main memory are shared. Of course, IO system is also there. So, here because of the constraint here, you see the constraint of L3 and main memory, so many processors are trying to access them. So, if you increase it to say 8, 16, 32, there will be lot of load on this L3 and main memory. Okay. So, there is a scalability issue, you cannot very easily extend it to larger number of cores or processors, because the memory bandwidth requirement will also increase, which is very difficult to do, right. Now, in this kind of an architecture, there is one feature is the memory access time for all processors is uniform. This is sometimes called uniform memory access or UMA. Why it is uniform? Because irrespective of which processor you are, the path to access memory is the same. So, the delay is the same, right. That is why it is called uniform memory access. But in contrast, loosely coupled multiprocessors look like this. There will be multiple processors with their own private caches. So, all L1, L2, L3 can be inside these. They will be having their local memories also and local IOs also. They will be connected via an interconnection network. So, here means a processor can access its local memory, and also via the interconnection network it can access the memory of the other processors. So, you can see the access time will not be uniform. Well, accessing local memory will be faster, but accessing the other memories will be slower, right. So, this is sometimes called non-uniform memory access or NUMA. This is also a cost effective way to scale memory bandwidth, because you see most of the time when you run a program on a core, a processor, it will be accessing its local memory only. Very rarely it will be trying to access the memory of the other processors. So, in this kind of architecture, even if we increase the number of processors, scalability will not be that much of a challenge. Okay? The overhead will not go up in a proportional way. So, the only flip side is that the communication between the processors is complex using that switching network and has higher latency. So, when you are mapping some applications to run on them, you try to map in such a way that most of the time they will be accessing the local memory and very rarely they will be accessing the other processors, their memories. Okay. So, in multiprocessors, this is one important problem. Of course, we are not going into the detail of this problem in this lecture, because it is a little beyond the scope. This cache coherency is a very important problem. You see, I am trying to illustrate this. Suppose I have two processors, let us say P1 and P2. Just assume they have their own cache memories, let us say C1, let us say C2. So, just ignore for the time being whether they are L1, L2 or anything, they are cache, and let us assume they have access to a common memory M. So, what might happen now, you see, there can be one block in this memory, let us call this is the block. The processor might be using this block. So, this block will be loaded in the cache. So, it is possible that the other processor is also trying to access this. So, this block will also be loaded in the cache. So, let us say B, this is the original block. So, a copy is here and a copy is here. Now, what might happen? The processor P1 might write something into this block B, which will make this block dirty. But as soon as it writes into B, what will happen? You can imagine these two blocks will become invalid. So, whatever is loaded in P2's cache, this will be a old or stale version of the block, because this block was recently modified, and the copy in memory will also be stale. So, this is called the cache coherency problem, where there are multiple copies of the block which may be located in several places. So, one of them may be the good version, others may be incoherent or the wrong versions. Okay? This is the basic idea. So, if you can see here, same memory block is loaded into two processor caches. One of the processor updates the data. So, data in the other processor cache and also memory becomes inconsistent. So, there are many methods and techniques that have been proposed to solve this problem. So, one is called the Snoopy protocol, where in the memory bus itself you continuously check whether someone is doing a write into its local cache. So, if it does, you immediately send the information to the other memory controllers also, so that they can check whether they are also having a copy of that same block in their cache. If so, they will immediately invalidate it, something like that. And directory based protocol is that where you store the information about the blocks in some central place where the memories are stored. So, you store that for a memory, this block is currently being held by these processors. So, in a processor update, you know that which are the other processors, they will also get affected. Okay? But I am not going into detail of these protocols here. So, I just tried to give you a very broad bird's eye view about what kind of parallel computing platforms are being used today and what are the different variations therein. Okay. So, with this I come to the end of this lecture. So, in this lecture, if you recall, we tried to give you a broad classification of computer systems with some examples, what kind of processing or computing systems fall under which category, and some of the problems and issues. So, if you are interested to know more detail on this, there are advanced level courses on computer organization architecture available. You will get to know about these in those courses. Thank you.